In this video, we will look at another topic, EtherChannel. EtherChannel allows you to group multiple physical interfaces into a group which operates as a single logical interface, so they behave as if they are a single interface. There are many benefits to this, and I'll explain them in this video. By the way, this video covers topic 2.4 of the official exam topics list, which states that you must be able to configure and verify Layer 2 and Layer 3 EtherChannel using a protocol called LACP, Link Aggregation Control Protocol. So what will we cover in this video? First off, I'll show you what EtherChannel is, and what problems it solves. Here's a hint. Spanning tree protocol is the big problem. We will also look at multiple methods of configuring both Layer 2 and Layer 3 EtherChannels. A Layer 2 EtherChannel is a group of switch ports which operate as a single interface, and a Layer 3 EtherChannel is a group of routed ports which operate as a single interface, which you assign an IP address to because it's Layer 3. Make sure you watch until the end of the video for a bonus question from Boson Software's XSIM, the best practice exams for the CCNA. I used Boson XSIM to help me prepare for my CCNA and CCNP exams, and I truly believe it was the key that allowed me to pass all of my exams on the first try. Okay, let's get started with the video. So let me demonstrate a problem. We have two switches here, A switch 1 and D switch 1. I will talk about basic network design later in the course, but A switch stands for access switch, which is a switch that end hosts like PCs and servers connect to. D switch stands for distribution layer switch, which is a switch that access layer switches connect to. For this demonstration, let's say there are many end hosts connected to A switch 1, let's say 40 hosts, and they are all trying to access the internet to do their work. The network administrator notices that the connection to D switch 1 is congested, so he decides that he should add another link to increase the bandwidth, so it can support all of the end hosts. So the network admin adds another link and monitors the situation. However, the additional link doesn't seem to help. The connection between A switch 1 and D switch 1 is still congested, and end users are reporting problems. So the admin decides to add another link between A switch 1 and D switch 1. He adds another link to the connection between A switch 1 and D switch 1. Surely, this will be sufficient. The total bandwidth of the connections to the end hosts is still greater than the bandwidth of the connection to D switch 1, but that's okay. All hosts in the network aren't always in a constant state of sending and receiving internet traffic. I will talk more about this later in the course. But when the bandwidth of the interfaces connected to end hosts is greater than the bandwidth of the connection to the distribution switches, this is called oversubscription. Some oversubscription is acceptable, but too much will cause congestion. However, even with 3 links to D switch 1, the congestion doesn't seem any better. So the network admin once again decides to add another link between A switch 1 and D switch 1. So now there are 4 links between A switch 1 and D switch 1. Do you think things have improved? Well, they haven't. The connection between the two switches is just as congested as before. Why is this? You should be able to figure out the answer. Here's a hint. Think about what you just studied in days 20, 21, and 22 of this course. If you know the answer, well done. If not, don't worry about it. You will now. Let's say the administrator went to physically look at the port lights of the two switches. What color do you think they were? Well, the network admin checks D switch 1 and all of the port lights are green, so there doesn't seem to be a problem. However, when he checks A switch 1, he notices that of the links connected to D switch 1, only one light is green and the others are orange. Why is that? It's because of what we studied in the past few days of this course, spanning tree protocol. If you connect 2 switches together with multiple links, all except one will be disabled by spanning tree. Why does it do this? Well, if all of A switch 1's interfaces were forwarding, Layer 2 loops would form between A switch 1 and D switch 1, leading to broadcast storms. Other links will be unused unless the active link fails. In that case, one of the inactive links will start forwarding. So, although having backup links is a good thing, because failures can occur for various reasons, it's a waste of bandwidth to have these three interfaces disabled, not forwarding any traffic. However, by forming these four physical interfaces into one logical interface, EtherChannel can solve this problem, giving us both redundancy and increased bandwidth. An EtherChannel is represented in network diagrams by drawing a circle around the interfaces that are grouped together, like this. EtherChannel groups multiple interfaces together to act as a single interface. STP will treat this group as a single interface. So after grouping these interfaces into an EtherChannel, the network admin once again checks the link lights. This time they are all green. Won't this cause a layer 2 loop? Actually, no, because this group of 4 links behaves as if it is a single link. For example, let's say a PC sends a broadcast frame. So it has flooded out all interfaces on A switch 1. All of the PCs connected to A switch 1 will receive a copy of the frame. Now, how many copies of the frame will D switch 1 receive? Remember, although there are 4 physical interfaces, they behave as a single interface. The answer is, D switch 1 will only receive 1 copy. This EtherChannel makes these 4 physical interfaces a single logical interface. A switch 1 won't send 4 copies of the same broadcast frame out of a single interface. Traffic using the EtherChannel will be load balanced among the physical interfaces in the group. An algorithm is used to determine which traffic will use which physical interface. I will give you more details on this later. So D switch 1 received the broadcast frame. What will it do now? It will flood the broadcast frame out of all interfaces, except the one it was received on. So let's say D switch 1 has these 2 other links here. Which interfaces will D switch 1 forward the frame out of? Only these 2. Why didn't it forward the frame out of the other 3 interfaces in the EtherChannel? I'll repeat it once more. Although this EtherChannel contains 4 separate physical interfaces, they behave as a single interface. D switch 1 won't send the broadcast frame back out of the same interface it was received on. So it isn't forwarded back to A switch 1, and no layer 2 loop is formed. It's kind of like this. Instead of 4 separate interfaces, perhaps gigabit Ethernet interfaces, connecting A switch 1 to D switch 1, it's as if there is a single 4 gigabit Ethernet interface. The bandwidth of the 4 separate interfaces is combined to form one faster interface, a virtual 4 gigabit interface. The difference between the physical characteristics and the logical or virtual characteristics of a network are something you need to understand as a network engineer. For example, we studied VLANs. Multiple PCs can all be connected to the same switch, and therefore be in the same LAN. However, VLANs virtually divide these PCs into separate virtual LANs, each behaving as a separate LAN. Likewise, these interfaces exist as 4 separate physical interfaces, but now they form a single virtual interface. Some other names for an EtherChannel are a port channel and a LAG, which stands for Link Aggregation Group. You'll see that to configure an EtherChannel in Cisco iOS, you need to use a few different terms. Now let's take a look at how EtherChannel load balances. It load balances based on flows. What is a flow? A flow is a communication between 2 nodes in the network. So, for example, between PC 1 and server 1. By the way, you usually won't see a server or a printer connected directly to a distribution layer switch. These are also end hosts, which you should connect to the access layer switches. Just to simplify this network diagram, I'll leave it like this though. So let's say PC 1 initiates an exchange of data with server 1, and it sends a few frames to do so. The frame is received by A switch 1, and assuming it already knows the MAC address of server 1, it will forward the frame out of the port channel to D switch 1. However, which physical interface will it use? Well, there is an algorithm it uses to calculate which physical interface the traffic will actually be sent on. Let's say it determines that this interface should be used. Now, when PC1 sends the next frame in the flow, in the communication between PC1 and server 1, the same interface will be used to forward the traffic to server 1. So the point is that frames in the same flow will be forwarded using the same physical interface. If frames in the same flow were forwarded using different physical interfaces, some frames may arrive at the destination out of order, which can cause problems. Some applications can deal with frames arriving out of order, but some applications can't. Now, if PC1 wants to print something and initiates a separate communication flow with printer 1, ASwitch 1 will once again forward the frame using its virtual port channel interface. However, it will make a separate calculation to determine which physical interface will be used for the flow. For example, it might determine that this interface will be used for the flow. Just like before, when PC1 sends another frame in the flow, the same member interface of the Ether channel will be used to forward it. How about if PC2 also wants to print something? It sends the first frame in the flow to ASwitch 1, which will then do a calculation to determine which physical interface in the Ether channel will be used. Perhaps this one is used. So this is how Ether channel performs load balancing, by using different physical interfaces in the Ether channel for different flows. The calculation that is done to determine which physical interface to use takes into account a few inputs. Actually, you can change the inputs used in the interface selection calculation. Here are the inputs that can be used. Source MAC address. So all frames with the same source MAC address will always use the same interface in the Ether channel. Or destination MAC address. In this case, all frames with the same destination MAC address will always use the same physical interface. You can also use both the source and destination MAC addresses. So for example, frames from PC1 to server 1 will always use a certain interface. Frames from PC2 to server 1 will always use a certain interface, which might be the same or different than the one used for traffic from PC1 to server 1. Frames from PC1 to printer 1 might use another different interface, etc. The calculation is done based on both the source and destination MAC addresses. You can also configure Ether channel to select the interface based on the source IP address, destination IP address, or both source and destination IP addresses. Some switches also support load balancing based on the layer 4 TCP or UDP port numbers, but those are a topic for another lesson. Also, which methods the switch can use depends on the switch model. Some may only support using the MAC addresses, some may support only MAC or IP addresses, and some may support all methods. So we haven't actually configured an Ether channel yet, but since I just mentioned it, let's take a look at how to check and configure the load balancing method. Use the command show Ether channel load balance to see the current load balancing method. You can see the default for this model of switch is to load balance based on the source and destination IP addresses. So, for example, all traffic from 10.0.0.1 with a destination of 10.0.0.2 will always use a certain physical interface within the Ether channel. Down here, you can see a more specific breakdown. Frames which encapsulate IP packets, whether IPv4 or IPv6, will be load balanced based on the source and destination IP addresses. However, notice at the top it says non-IP will use the source and destination MAC addresses. Well, that's because if an IP packet isn't encapsulated in the Ethernet frame, there is no IP address that can be used to determine the load balancing. So the MAC addresses are used instead. Now, as for how to change the load balancing method, enter global config mode and use this command: port channel load balance, followed by the method. In this case, I changed it to use the source and destination MAC addresses of the frame. Then I confirmed once more, and you can see the load balancing configuration has been successfully changed. By the way, here are the choices available on this device. It can load balance based on MAC or IP addresses, and in either case it can load balance based on either the source, the destination, or both the source and destination addresses. Now, I want to point out one thing which is a little frustrating about Ether channel configuration on Cisco devices. What keyword do you use to configure the load balancing method? Port channel. And what keyword do you use to view the load balancing method? Ether channel. Different words are used for the same thing, which is a bit frustrating. Actually, later, you'll find that there is even one more that you need to remember. So these are the first two commands to remember for this video. Show EtherChannel load balance to check the load balancing method being used, and port channel load balance, followed by the load balancing method, to configure the load balancing. Now let's get into actually creating an EtherChannel between two switches. There are three methods of EtherChannel configuration. First up is PAGP, which stands for Port Aggregation Protocol. It is a Cisco proprietary protocol, so it can only be used on Cisco switches. If you're trying to form an EtherChannel with a Juniper switch, for example, you can't use PAGP. Now, what does PAGP do? It dynamically negotiates the creation and maintenance of the EtherChannel. Just a few days ago, we covered DTP, which does a similar thing regarding trunk formation. Frames are sent to the neighboring switch to see if it wants to form an EtherChannel, and then the switches agree upon either forming an EtherChannel or not. Okay, the next method of configuration is LACP, which stands for Link Aggregation Control Protocol. It is an industry standard protocol, once again from our friends at the IEEE. Its code is 802.3 AD. Basically, it does the same thing as PAGP. It dynamically negotiates the creation and maintenance of the EtherChannel, like DTP does for trunks. Because it is an industry standard protocol, it doesn't run only on Cisco switches, so it can be used to form EtherChannels with switches from other vendors. Because of this, LACP is the preferred method of configuring EtherChannels. Actually, the exam topics list only states LACP. However, for the test, you really should be familiar with the other methods. For some reason, Cisco's exam topics lists aren't very reliable. So the last method is static EtherChannel. In this case, a protocol isn't used to determine if an EtherChannel should be formed. Instead, interfaces are statically configured to form an EtherChannel. This is usually avoided because you want the switches to dynamically maintain the EtherChannel. For example, you want the switch to remove an interface from the EtherChannel if there is some sort of problem on the interface. Okay, finally, up to 8 interfaces can be formed into a single EtherChannel. Actually, LACP allows up to 16, but only 8 will be active. The other 8 will be in standby mode, waiting for an active interface to fail. So let's look into how to configure each method. The configuration for each is almost identical. You just have to swap out some keywords. First, I used the interface range command to configure all of the member interfaces at once. This is a good idea for EtherChannel, because the configurations on each member interface must match. So if you configure them all at once, you can guarantee that. I'll talk more about that after I show you the configurations. Anyway, to actually configure the EtherChannel, use this command, with yet another new keyword. Channel group, followed by a number that identifies the virtual interface, mode, and then as you can see, I use the question mark to see what options there are. There are 5 options. 2 of them are used for PAGP, 2 for LACP, and 1 for static EtherChannel. These 2 are used for PAGP. Do you recognize these names from another Cisco proprietary protocol? DTP used the same modes to form trunks, and the function of each mode is basically the same. Desirable mode actively tries to form an EtherChannel, and auto mode will only form an EtherChannel if the other side is set to desirable, but not if the other side is set to auto. So here's a summary. If both sides of the connection are set to auto, no EtherChannel will be formed. However, auto and desirable, or desirable and desirable, will form an EtherChannel. Anyway, I decided to configure this side as desirable. You can see that the virtual port channel interface was created, with the number we used in the channel group command. You can see it here in the output of the show IP interface brief command, down at the bottom. So remember that the channel group command is used to configure the EtherChannel, but the name of the virtual interface that is created is port channel. By the way, this channel group number has to match between interfaces on the same switch. However, it doesn't have to match the channel group number on the other switch. For example, channel group 1 on A switch 1 can form an ether channel with channel group 2 on D switch 1. The number is just used to identify the virtual interface number on the local switch. Because you can have multiple ether channels on a single switch, you need the number to identify them. Next, let's look at LACP configuration. After explaining all of that, there's not much else to explain about LACP. Just notice that mode names are different. Instead of desirable, LACP uses active mode. And instead of auto, LACP uses passive mode. So if both ends are configured in passive mode, an ether channel won't be formed. However, active and passive, or active and active, will form an ether channel. In this case, I configured this side as active. Once again, the port channel interface is created. Note that, even if you configure both sides as passive, the virtual interface will still be created on each switch. However, it won't actually be functioning as an ether channel, unless one side is in active mode. So as you can see, the command is basically the same, just the mode names are different. Once again, the channel group number has to match between member interfaces on the local switch, but it doesn't have to match the number on the neighbor switch. Finally, let's see how static ether channel is configured. There aren't two separate modes, just one, on, which manually tells these interfaces to form an ether channel. This will create a port channel interface just like before. By the way, on mode only works with on mode. On and desirable, or on and active, will not successfully form an ether channel. Another command you should know is the channel protocol command. This manually configures the ether channel negotiation protocol that the member interfaces should use. This actually isn't a very useful command because you don't need to configure it. If you configure channel group 1 mode desirable or auto, the interface will automatically use PAGP. Or if you configure channel group 1 mode active or passive, the interface will automatically use LACP. So there isn't really a point in using this command. However, I think you should know it for the exam at least, so here's a brief explanation. Of course, there are two options, LACP and PAGP. I decided to configure LACP. Then I tried the channel group 1 mode desirable command, but it was rejected because of the protocol mismatch. I manually configured these interfaces to use LACP, but the desirable mode is PAGP, so the command was rejected. If I try channel group 1 mode on, it is rejected as well. Then I do channel group 1 mode active, and the command works because active mode is LACP. So after configuring the ether channel in whatever mode, PAGP, LACP, or static, you can then configure the port channel interface itself. Note that I'm just using the LACP example here, since all of this information is the same, regardless of which method you use. I also did the same configurations over on D switch 1, so the ether channel is up and running. I entered interface config mode for the port channel 1 interface, and then configured it as a trunk. Now in the output of show interfaces trunk, you can see port channel 1, listed as PO1, is a trunk. Notice that the individual physical interfaces aren't listed here, only the port channel interface. Here's a section of the output of show running config. There's something interesting to notice here. The trunk configurations that I configured on the port channel interface were also applied to the physical interfaces. I didn't manually configure the physical interfaces as trunks. Now, one more important point about ether channel configuration. Member interfaces, the physical interfaces in the ether channel, must have matching configurations. What do I mean by that? They must have the same duplex setting. They must have the same speed. They must have the same switch port mode, meaning access or trunk. If they are a trunk, they must have the same allowed VLANs and native VLANs. If an individual interface's configurations do not match the others, it will be excluded from the ether channel. When it comes to verifying the status of an ether channel using show commands, the most useful command is show ether channel summary. Down here is a list of the port channel interfaces on the switch. Next to port channel 1, it has two flags, an uppercase S, and uppercase U. To check the meaning of these, look at the legend up top. S means it is a layer 2 ether channel. S stands for switch port, by the way. U means in use, meaning the ether channel is active and being used. Next to the physical ports, there is the flag P. This means that these ports are properly bundled in the port channel. These are the flags you want to see in an operational layer 2 ether channel. Now, let's take a look at a couple situations in which we will see other flags. So, I shut down the port channel 1 interface. Now, next to both the port channel interface and the member interfaces, you can see the flag D. That means down. Okay, I'll enable the interface again and show you another flag you might see. Now I changed one of the member interfaces to access mode. Now it has the lowercase s flag. Note that this is different than the uppercase s flag. It means suspended. So, only G00 is suspended, but the ether channel is still operating with just 3 interfaces, G01, 2, and 3. Another command you can use is show ether channel port channel. You can see the number of ports in the ether channel, which protocol is being used, etc. One important bit of information that you can't find in show ether channel summary, but is displayed in this command, is the channel group mode, active in this case, because I used the channel group 1 mode active command earlier. However, for ether channel, the most common command you're going to be using is definitely show ether channel summary. I just wanted to show you one other option. Because I started this video talking about spanning tree, let's see how it is affected when ether channel is configured. As you can see, only the port channel interface is listed. The physical interfaces do not appear in the output of this command at all. So, as I said earlier, spanning tree is treating these 4 physical interfaces as a single logical interface. Instead of blocking 3 of them, they can all forward and receive traffic, with no worry of layer 2 loops. To close off this lecture, let's take a brief look at layer 3 ether channels. I've replaced A switch 1 and D switch 1 with multi-layer switches. Instead of a layer 2 connection between them, let's use a layer 3 connection. Modern network design often leans toward using layer 3 connections between switches, because that way, spanning tree won't be an issue anywhere in the network. We could have 4 switches interconnected in a mesh, and if we're connecting them with layer 3 routed ports, all interfaces will be up and forwarding. None will have to be disabled due to spanning tree. Now you may be thinking, didn't you just show that ether channel means that spanning tree doesn't have to block any ports? Well, we're just looking at a connection between 2 switches. Even if we're using ether channel, layer 2 loops can still occur if multiple switches are connected together in a loop. For example, look at this diagram. All of the connections between switches are using ether channel. But if we don't block any of the port channel interfaces, broadcasts can still loop around the switches like this and cause a broadcast storm. So, spanning tree will block one of these port channel interfaces. However, if all of these connections between switches were made using routed ports, not layer 2 switch ports, there is no need to run spanning tree at all. Routed ports don't forward layer 2 broadcasts, so no layer 2 loops can be formed. We already know how to configure routed ports with the no switch port command. Let's see how to configure a layer 3 ether channel. So, starting from a clean configuration, no port channels have been configured yet on A switch 1. I enter interface range config mode for the member interfaces, and this time before using the channel group command, I use the no switch port command to make them layer 3 routed interfaces. Then, after using the channel group command, I used show running config to check the config. Notice that the port channel interface that was created has the no switch port command applied to it automatically. Now, since we're making a layer 3 ether channel, we need an IP address. Where do you think it should be configured? It should be configured on the port channel interface. So, there it is. Now let's check the show ether channel summary command once more. So the only difference in the output is that instead of the uppercase S flag, it has the R flag. What does that mean? It means it is a layer 3 ether channel. R stands for routed port. In the output of Show IP Interface Brief, you can see the IP address configured on port channel 1. So now A switch 1 and D switch 1 are like two routers connected together. They are connected at layer 3, and spanning tree is not running on the connection between them. However, just like with the layer 2 Ether channel, traffic will now be load balanced over the 4 member interfaces. Okay, let's quickly review the commands we covered. First is port channel load balance, followed by the mode, which depending on the switch model, can involve MAC addresses, IP addresses, or layer 4 port numbers, using either the source, destination, or both source and destination in the calculation to determine which physical interface is used to forward any specific flow of traffic. To view the current Ether channel load balancing configuration, use Show EtherChannel Load Balance. To configure an interface to be part of an Ether channel, use the command channel group, followed by the port channel number, mode, and then the mode, which can be desirable, auto, active, passive, or on. The most useful show command for Ether channel is Show EtherChannel Summary, displaying a summary of all of the Ether channels on the switch and their status. One more show command you can use is Show EtherChannel Port Channel, which displays some more detailed information about the port channel interfaces on the switch. Those are all of the commands we learned today. Of course, there are many more commands that can be used, but we don't need to go any deeper into the concept of Ether channels. As long as you understand their basic purpose and how to set them up and verify their status, you should be good for the CCNA. Okay, let's go to today's quiz. Watch until the end of the quiz for a bonus question from Boson XSIM for CCNA. Without a doubt, the best practice exams for the CCNA, and the ones I used when preparing for my CCNA and CCNP exams. Let's go to question 1 of the quiz. Which of the following channel group mode combinations will result in an operational Ether channel? Choose 3. A. On. B. Passive. C. Desirable auto. D. Auto. E. Active desirable. F. On desirable. Or G. Active. Pause the video to think about your answer. The answers are A, C, and G. A, on, creates a static Ether channel, which doesn't use PAGP or LACP to negotiate the Ether channel. C, desirable auto, creates an Ether channel using PAGP. G, active, creates an Ether channel using LACP. So A, C, and G are the correct answers. B, passive won't create an Ether channel because LACP passive mode doesn't actively try to form an Ether channel. Same for D, PAGP auto mode doesn't actively try to form an Ether channel. E, active desirable, and F, on desirable, makes two different Ether channel modes, which won't result in a valid Ether channel configuration. Let's go to question 2. In the output of the Show EtherChannel Summary command, you notice that the physical interfaces in the Ether channel you configured have the flag P next to them. What does this mean? A. The interfaces are in LACP passive mode. B. The interfaces are bundled in the port channel. C. The interfaces are paused until the other switch's Ether channel is configured. Or D. The Ether channel is a layer 2 Ether channel. Pause the video to think about your answer. The answer is B. The interfaces are bundled in the port channel. This is the flag you want to see next to the member interfaces of an Ether channel. Here's some sample output of Show EtherChannel Summary. As you can see, P means the port is bundled in the port channel. Let's go to question 3. Which of the following member interface parameters need to match to form an Ether channel? Choose 2. A. Interface ID. B. IP address. C. Interface speed. Or D. Switch port mode, access or trunk. Pause the video to think about your answer. The answers are C. Interface speed and D. Switch port mode. These are two of the settings that have to match for interfaces to form an Ether channel. A, interface ID, is unique to each interface, so it cannot match. And even if you're configuring a layer 3 Ether channel, the member interfaces won't have IP addresses. The IP address must be configured on the virtual port channel interface. So B, IP address, is also incorrect. Okay, next let's take a look at a question about Ether channel from Boson XSIM for CCNA. Okay, for today's Boson XSIM practice question, we have a question about Ether channel. And this is a really good question, quite challenging. So let's take a look. You issue the following commands on switch A and then on switch B, so there are two switches. So let's see the commands. First, interface port channel 1. So this isn't necessary, but it creates the port channel in advance before actually doing the interface range command. So this virtual port channel exists. The interface exists, but no physical interfaces have been made members of that virtual interface. Okay, then we enter the interface range command for Fast Ethernet 05 and 6. We manually configure the channel protocol, the negotiation protocol, LACP in this case. And then finally, we use the channel group 1 mode on command. Now normally, as I showed you in this video, when you use the channel group command, the port channel interface is automatically created. So this isn't always necessary. Okay, so that's switch A. Channel protocol LACP, channel group 1 mode on. How about switch B? Again, we create the virtual port channel interface beforehand. Enter interface range config mode for Fast Ethernet 05 and 6. This time we manually configure the protocol as PAGP, before once again doing channel group 1 mode on. So which of the following statements is true about the resulting Ether channel link between switch A and switch B? Select the best answer. A link is formed using LACP because it was configured first and has priority. As you can see here, LACP was configured first. B, no link is formed. Okay. C, a link is formed using PAGP because it was configured last and has priority. So it was configured here on switch B. And then D, a link is formed without an aggregation protocol. So you see both of these switches use the command channel group 1 mode on. This configures static protocol without an aggregation protocol. So what do you think is the answer? Pause the video here to think about it. Okay, hopefully you got the answer. I think the correct answer is B, no link is formed. Now, why is that? So first you create the port channel interface. So it does exist, the virtual interface. Then you manually configure the channel protocol on the physical interfaces. But when you use the command channel group 1 mode on to tell these physical interfaces to join this port channel interface, to join the Ether channel, this command will be rejected, the channel group 1 mode on command, because we already manually configured LACP. So the only modes you can actually configure are active and passive. Mode on will not work. The command will be rejected. And then same thing on switch B, but this time instead of LACP, it's PAGP. So you manually configured the channel protocol, PAGP. So even though this port channel interface exists, these interfaces won't actually join it because the channel group 1 mode on command will be rejected. So I think B is the correct answer. Let's check. And indeed it is. So here is Boson's explanation, quite a lengthy, in detail explanation. And this is something really great about XSIM. If you're ever unsure about why B is correct or why A, C, and D are incorrect, we've got all of these great in detail explanations helping you out. And then finally at the end, there are references. This is to the official cert guide. Ether channel is covered in volume 1, chapter 10. And then also 2 links to Cisco documentation, which is freely available online and is also a great study resource. Okay, so that's today's Boson XSIM practice question. If you want to get a copy of Boson XSIM, please follow the link in the video description. I really like these practice exams. I use them myself for my CCNA and CCNP, so I really feel confident about recommending them to you. So once again, follow the link in the video description to get a copy of Boson XSIM. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab, so you can get some hands-on practice. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course.